Hi everyone, welcome back. In this video, I will discuss the solution to the problem 2 swaps. In this problem, given a permutation of sum of the first natural numbers, that is basically n, the permutation of n, all the integers from 1 to n with the frequency exactly equals to 1 in an array ARR, and you have to determine if the array can be sorted in exactly 2 swaps. This term is very important, in exactly 2 swaps. And a swap can involve the same pair of indices twice, that is you can select the same pair of indices twice. So I can also say that we have to sort this array in exactly 2 or 0 swap. If we were required a 0 swap, then what I will do, I will select the same pair of indices twice and swap its element 2 times, so that the array will remain as it is. And we have to return true if we can sort this array with exactly 2 swaps or 0 swaps, and otherwise false. Cool. So let's see how we can solve this problem with the multiple test cases. So the very first thing, we are given a permutation of n. Here n is the size of the array, that is all the integers from 1 to n with a frequency 1. And to sort this array, that is a shorted version of this array, all the elements from 1 to n, that is first we have a 1, then 2, 3, 4 and up to n. Cool. So I can say ARR of I must be at index I minus 1. This is the correct position of ARR of I. Here I am considering the zero based indexing as per the implementation. Cool. So let me write some test cases. So let's say the given array is already sorted. So 1, 2, 3 and 4. The value of n is 4, that is permutation of 4, all the integers from 1 to 4. So in this case, how we can solve this problem with exactly 2 swaps? How we can sort this array with exactly 2 swaps? So first I will select these two indices, that is these two elements you can also say, and then again I will select these two elements, so that first they will swap, and once you again perform the operation, then they will move to its correct position, that is original array. So in such type of case, when the array is already sorted, we have to return true. Now let me give you another example. So let's say we have 1, then 3, then let's say we have 4 and then 2. So in this case, how we can solve this problem? So first what I can do, I can swap these two elements, that is I will move this 3 to its correct position. So here we have 4 and then 3. Then what I will do, I will perform another operation and move this 3, move this 2 to its correct position, and 4 will automatically move to its correct position, which is index 3. Cool. So that is a 2 comma 4, and we can solve this problem with exactly 2 swap. We can sort this array. So here also I will return true. Now let's discuss a very interesting case. Here let's say we have 1, then what I can say, let's say we have 3, then 2 and then we have 4. So in this case, I will move this 3 to its correct position, that is I will swap these two elements. So after swapping these two elements, this will be your new array 1, 2, 3 and 4. And now you are left with one swap. So where do you perform one swap? One swap. So we cannot sort this array with exactly two swaps. We can sort this array in one swap, but not in two swaps. So in such type of case where the number of swaps required is 1, I will return false. Cool. Now let me discuss one more case here. So let's say we have 4, then 3 and 1, 1 and 2. Cool. And also let me write indices as per the zero based indexing. So index 0, then index 1, index 2, index 3. So here we have to find the length of cycles in a permutation. And to get this thing, I will find the correct position of every element. And what will be the correct position of every element? So the current element ARR of I must be at index I minus 1. This is the correct position of element ARR of I. I can draw in terms of these indices. I can draw in terms of a graph. So I can say the element which is at index 0, its correct position is index 3. So I can say there is an edge from 0 to 3. And the element which is at index 3, it is 2, and its correct position is index 1. AR of I must be at index I minus 1. And the element which is at index 1, it is 3. Its correct position is a 2, index 2. We must have this 3 at index 2. Cool. And the element which is at index 2, it is 1. Its correct position is 0. So you will get this cycle, and for every index I you will get a cycle either of length 1 or up to n. Cool. And to solve this cycle, that is to move all the elements to its correct index, you require length of the cycle minus 1 swaps. That is, let me write it over here. Number of swaps required is the length of the cycle. So I can say cycle length and minus 1. So for this particular case, it is 3. Cool. And let me just quickly depict this, depict all the 3 swaps with same example. So first what I will do, I will move this 4 to its correct position. And to how we can move this 4. So just simply swap ARR of I, comma, ARR of I minus 1. So just simply swap ARR of I, which is 4, and its correct position is I minus 1, that is 4 minus 1, 3. So ARR of I minus 1, and minus 1 because of the zero based indexing. Cool. So for the first operation, this 4 is not its correct position. So I will move this 4 to its correct position. That is, I will simply swap 4 and its correct position is 3. That is ARR of 4 minus 1. So I will swap these two positions, these two elements. So the new array will be 1, not 1, but 2, then 3, 1 will remain as it is, and then element 4. Now I have moved this 4 to its correct position. That is, each operation of swapping will move one element, at least one element, not at least, but exactly one element to its correct position. And then how many times I will perform this operation? I will perform this operation until the current index will not have its correct element. So while ARR of I not equal to I plus 1, that is, you can also say ARR of I minus 1 must be at index I. Cool. And while this condition is false, true, that I will swap the element, that is move the current element to its correct position. So then after we have 2, and this index 0 is not its correct position. So I will move this 2 to its correct position, that is swap, comma, ARR of 2 minus 1, that is 1. Move this 2 to its correct position. So here in this case, the new array will be, the new array will be 3 and 2, which is now at its correct position, then 1 and 4. Cool. And now we have now we have element 3 at index 0, and this is not the correct position of element 3. So I will move this 3 to its correct position, that is swap 3, comma, ARR of 3 minus 1, which is 2. Cool. I will swap these two elements, and after this I will just simply get 1, 2, 3 and 4, and this is the sorted array. And how many swaps we require? We require 3 swaps, and this number is greater than 2, so my answer is false. So this is the complete explanation. And how much time it will take if I do this thing for all the indices? So it will take order of n time. And why it is order of n? Because in each iteration of this while loop, I am moving the current element to its correct position. That is, I'm moving the element to its correct position in each iteration of this while loop. So this will run at max n times, and n iteration of this outer loop, that is for I is equal to 0 to n minus 1, and for every index I will perform this step. So that's why it is order of 2n at max, or can be written as order of n. Now let me just show you the implementation. So here is the implementation: size of the array, then number of swaps, which is number of swaps required, and iterate from all the indices from 0 to n minus 1. And if the current element is not its correct place, if this is not the correct place of the element AR of I, then I will perform the swap operation, move the element to its correct place, and increment the value of count, that is the number of swaps required. And at the end, I'm just simply checking if the number of swaps required is 0 or 2, then I will return true, otherwise false. Cool. So successfully submitted. And thank you so much guys for watching this video, and have a good day.